Hello everyone and welcome to lab number 7. Lab number 7 deals with vorticity, and this little PowerPoint presentation, this little video, deals with vorticity advection. So whenever we talk about advection, we're talking about bringing a property into an area and the movement of some property. And we discussed temperature advection last lab. This lab, we're looking at the property of vorticity, and vorticity can move. As the air moves along, the spin moves with it. So if you're standing at a given location and you're seeing the air spin up or spin down, one reason could be because of advection, bringing air with higher spin or lower spin into a local area. So we're looking at how the air spins up or spins down at a given location over time. And that funny ziggle, whatever it looks like, that's a zeta. So zeta is relative vorticity. In this lab, we're dealing more with absolute vorticity advection. But we can also talk about relative vorticity advection. They're just slightly different. So we'll look at, in this PowerPoint or this video, we're going to look at how the relative vorticity changes at a given location over time. So, here's the equation. Remember, this is your total or Lagrangian derivative, which tells you that as you move along with a parcel of air, as you're moving along, you can see the changes in the spin. And the changes result from local changes and also the gradient as you're moving along, looking at, as you move along, seeing changes as you move along. Well, we can rearrange this equation, and also we can assume that the parcel of air as it moves along doesn't really spin up or spin down. So that's going to be one of our assumptions. We assume that vorticity is conserved following a parcel. It doesn't really spin up or spin down. So we'll do that. That makes the big dt dz or d zeta dt 0. So another assumption we're going to make is that the vertical advection of vorticity is also small. So can you spin, brings air up or down with different spins? Yes, you can, but we're going to assume for synoptic scale motions that's really negligible. We made these two assumptions also with temperature advection, if you remember. So what that leaves us with, it tells us that the local spin, and this is the equation on the bottom, the local spin, the relative vorticity, the local spin changes with time as a result of the advection of vorticity, bringing air in that has different spin properties. So looking at that right side of the equation, you got d zeta dx, that's how the spin or vorticity changes in the x direction. D zeta dy is how it changes in the y direction. Basically what that is if you put that on a map, that's your gradient. That's your gradient of vorticity. And then the u and v are components of the horizontal wind. We're going to call that a big V. So here's our equation now. The horizontal vorticity advection equation says that the local change in vorticity is equal to the negative of the velocity of the wind, and that's a dot product with the gradient of vorticity, horizontal gradient of vorticity. So we're looking at local changes as a result of advection. So if you break this down, if you remember, we can break down into the magnitudes of those two things, the two things being the magnitude of the wind and also the magnitude of the vorticity gradient, and then the angle between the two, because remember those are both vectors, so there's got to be an angle between those. So the angle between the gradient and the wind will tell you how much advection you're getting, vorticity advection. So what we're going to do is we're going to look at a flow field. Here we got a vortex. It's just spinning more in the center. That's where you got maximum angular rotation, and spinning less on the outside, less degrees per second or per minute or radians, degrees, whatever. But it's spinning greater in the middle and less at the outside. So remember, gradients always point towards greater values. So the arrows for gradient, the gradient of vorticity, are pointing towards the center. That's where it's spinning the most, spinning the fastest. And then let's say that we have wind that is blowing through this gradient. And the wind is going from the west to the east, just to make it really simple. What we're going to do is we're going to look at 3 locations. We're going to assess the vorticity advection in those 3 locations. So here you can see there's an angle between the vorticity gradient and the wind, and the angle varies depending upon where you are. So let's take a look at the top. And here the wind is moving, of course, west to east, but the gradient is pointing straight towards the max and it's pointing straight down. So that means you got a 90-degree angle between these two. And you know the cosine of 90 is 0. So if you stick that into the equation, the whole right side of that equation will be 0. The cosine of 0, the cosine of 90 is 0. So that means that there is no vorticity advection. And that makes sense. If you look at the arrow, the wind, you can see that it's kind of blowing parallel to the isoplus of vorticity. And if the wind is blowing parallel to isoplus, there's no advection occurring. Let's take a look at another case. And this is on the west side. The wind is blowing from the west to the east. And you can see that the gradient in vorticity is pointing towards the maximum. And the angle is 0. It's very small. It's 0. So the cosine of 0 is 1. So if I stick 1 in there, I get a negative number for the left, or for that value. And what that means, a negative means that it's negative vorticity advection, and we also call that anticyclonic vorticity advection. We'll leave it at negative right now, or NVA. And then on the other side of the spin, if you've got the wind blowing through this vortex and you've got the gradient of vorticity pointing towards the maximum, you can see those two angles are 180 degrees. And the cosine of 180 degrees is -1. If I stick a -1 in there, since there's a minus sign out in front of the V, that whole thing on that whole equation now is positive, which means you have positive vorticity advection, also cyclonic vorticity advection. Sometimes this is kind of hard to visualize, but what's going on here is the wind is blowing maximum values to regions where there's minimum values of spin or vorticity. So that gives you a little bit of insight. So typically what you're going to find is positive vorticity advection downwind of troughs or in troughs. And then negative vorticity advection downwind of ridges, because in the trough you're going to find positive vorticity, very cyclonic because of the curvature, and just the same very negative in the ridges because of the curvature. So here's a map showing you that, and this is from a long time ago. This is from 2000. I probably should get a more recent one. But it does have good examples of ridges and troughs, and you can see where the troughs occur. You see you have the hatched red areas, which is indicating very high vorticity. In this case, 26 times 10 to the -5th. I think that's the units that they use, radians per second. So also in ridges, you can see that it is slightly positive or maybe even negative, because what's plotted on this map is absolute vorticity, which is the Earth's plus the relative vorticity. This is what it looks like in black and white the same day. Sometimes on exams it's hard to put color charts, so I'd like to put black and white. Not only that, but also they have isoplus on here of vorticity, and the isoplus are dashed, whereas on this 500 millibar map the solid lines are height lines. Remember that winds blow in the upper atmosphere parallel to the contours because the wind is geostrophic. You learned that way back in 110. We'll talk more about that later on. But you can see the wind actually blowing through these regions of vorticity, producing either positive, negative, or no vorticity advection. So typically, and this is something that I have in the lab document, something very similar to this, but it shows you the angle between the gradient and the angle between the wind that results in positive vorticity advection ahead of troughs. You could also do it in color if you like. Also here it shows negative vorticity advection downwind of ridges where the angles are very close to each other also. The angles are less than 90 degrees. You can do it in color too. And I think that's all I have for you now. So I'll see you in lab, or I'll see you in lecture. Take care.